Good morning! Today's lesson is on creative thinking, our learning objectives. At the end of the session, we should be able to explain out-of-the-box thinking, apply Scamper to idea generation, and formulate a mathematical model. Let's recall Polya's heuristic. Step 1, understand the problem. Step 2, devise a plan or a strategy. Step 3, implement the plan. Step 4, review your answer or look back. The Art of Problem Solving was written by Russell Ackoff. It provides an excellent non-quantitative description of this management science approach for a variety of societal problems. The introductory puzzle illustrates the process of creative problem solving. Let's look at it. Suppose you have a piece of paper containing 9 dots. Draw 4 straight lines without lifting the pen or pencil from the paper so that all 9 dots are covered by the lines. Is that difficult? Let's look at the solution to the 9-dot problem. Did you notice that there is an imaginary box that contains the 9 dots? And to solve the problem, you have to start at one corner of the box and then you go way past that box. This is referred to as outside-the-box thinking or creative thinking. So what does it mean to think out of the box? That means we think differently, we think unconventionally, and from a new perspective. We examine the assumptions carefully. Maybe we should try to think out of the box. Why? Because that leads to the innovation department. Steve Jobs represents out-of-the-box thinking. Now let's look at a classic puzzle. How can you plant 10 flowers in 5 rows and have exactly 4 flowers in each row? Does that seem impossible? Well, let's redefine row. Here's the solution. You plant the 10 flowers at the 5 corners and at the 5 intersections of a pentagram star. Recall your geometry. Pentagon is a 5-sided polygon. Then we construct the star, pentagram star, and then we plant the flowers. That's out-of-the-box thinking. So how do we develop our capacity for out-of-the-box thinking? We need to ask questions. So let's consider some questions that can spark the imagination. Someone asked, why can't there be a reliable overnight mail service? That's Fred Smith, founder of Federal Express. Geoffrey Hounsfield asked, why can't we see in 3 dimensions what's inside the human body without cutting it open? And the CAT scanner was invented. What happens if I pour rubber into my iron waffle? Bill Bowerman asked, and Nike was born. What can we do if we take an object and break it down and fragment it into so many different parts? Asked Pablo Picasso, a Spanish painter. He is the founder of the Cubist movement that revolutionized European painting and sculpture and inspired related movements in music and literature. So how can we improve our idea generation abilities? We can look at Osborne's checklist for idea generation. Okay. Using the acronym Scamper, we can ask questions starting with each of the letter. Starting with letter S, okay, what can I substitute? Letter C, what can I combine? Letter A, what can I adapt? Letter M, what can I modify or magnify? Letter P, what can I put to other uses? Letter E, what can I eliminate or minify? And letter R, what can I rearrange or reverse? So you use Scamper for idea generation. Albert Einstein said, imagination is more important than knowledge, because knowledge is limited and imagination encircles the world. Einstein said, the formulation of a problem is often more essential than its solution, which may be merely a matter of mathematical or experimental skill. To raise new questions, new possibilities, to regard old problems from a new angle, requires creative imagination and marks real advances. Now, let's look at the general optimization problem. We have the real-world system, and we formulate a model abstracted from the real situations. We identify and focus on the dominant factors that control the behavior of the real system. So what are the elements of mathematical models? We have decision variables representing the unknowns, the objective function to be optimized, and the constraints, which are the limitations of the system. Then we look for the optimal solution, which is a set of variable values which are feasible solutions that lead to the optimal values of the objective function. Let's look at an example, the problem of controlling pollution. A manufacturer of a chemical product has two plants where the product is made. Plant 1 can make at most 30 tons per week. Plant 2 can make at most 40 tons per week. The manufacturer wants to make a total of at least 50 tons per week. The amount of particulate matter found weekly in the atmosphere over a nearby town is measured and found to be 20 pounds for each ton of the product made by plant 1 and 30 pounds for each ton of the product made at plant 2. The decision problem. How many tons of the chemical product should be made weekly at each plant? The goal? To maximize the total amount of particulate matter in the atmosphere. Let's formulate the model. First, we define the decision variables clearly. Let's try to formulate the model. First, we define the decision variables clearly. Let X denote the number of tons made at plant 1 and Y denote the number of tons made at plant 2. Next, we determine the quantity to be optimized and express it as a mathematical function. We want to minimize pollution, so we minimize Z is equal to 20x plus 30y. Then, we identify all stipulated requirements, restrictions, and limitations, and express them mathematically. These requirements constitute the constraints. The production constraints are as follows: X less than or equal to 30, Y less than or equal to 40, and X plus Y greater than or equal to 50. We express the hidden conditions as the non-negativity restrictions. X should be greater than or equal to 0, and Y greater than or equal to 0. So the complete model for the pollution control problem is as follows. Minimize Z equals 20x plus 30y subject to the production constraints and the non-negativity restrictions. Notice that all of the expressions involved here are linear. So we refer to this model as a linear programming model. It's a branch of a field called operations research, or science of better, or management science. Operations research, or OR, is the discipline of applying advanced analytical methods to make better decisions. It is characterized by its broad applicability, by its interdisciplinary nature, and the wide variety of career opportunities and work styles it embraces. I invite you to look at this site. The OR Inside exhibition tells us how OR shapes the world around us. It gives us examples of how OR is inside just about everything we do, even though we can't see it. Now, how do we solve linear programming problems? We can either graph the solution. If we have only 2 or 3 variables, we can do that. But in the real world, we have many variables and constraints. So we may resort to using a software, and you can take a look at this. It's based on George Danzig's simplex algorithm. Recall our lesson on natural optimizers. The bees know how to minimize and maximize. Their structure for the honeycomb is hexagonal because the shape allows the maximum space and uses the least amount of wax. Go ahead, think outside the box, keep asking questions, formulate models, solve problems, and improve systems.